Welcome back to my YouTube channel. This is lecture number 6 of PLL series, and in previous lecture we have seen the locking condition of PLL, which was delta omega 0 by k must be less than 1. So that was the condition for locking the PLL, and we saw one equation that the phi error, the differentiation of phi error by k was equal to del omega 0 k minus sine phi error, that should be equal to 0. Then PLL will only lock, right? Because the locking condition says that differentiation of phase error should be equal to 0. So that equation should be equal to 0. Okay. And for making this equation 0, there should be some solution point of phase error, right? What I want to say, I'm saying that if I'm plotting this equation, okay, if it is a phi error and this is your phi error dash by k, so this sign will reverse and see, you can see there are some solution points. Okay, so this must be there. Okay, so that's why I'm saying that it should be equal to 0. Now that was a case of PLL law, and now I'm giving the second case if this condition is not satisfied. I mean, if del omega 0 by k is greater than 1, what does it mean? So see, in this below plot you can see that this is the value of del omega 0 by k, right? Okay, that much shifted. And you also know that the amplitude here of sine phi error is 1. That means it is 1. This is 1. So what do you think? This is less than what? Del omega 0 is by k less than 1. Then only we are able to get this solution point. If it is greater than 1, then what? So your waveform will shift like this, and this will be your 1. That is the value of del omega 0 by k. And since the amplitude of sine is 1, so it will go like this, right? So it will remain here only, so it won't cross this axis. So you can see that there is no solution for this equation. What does it mean? It means that PLL won't lock. Okay, so I hope this much is clear. Okay, so what was the condition? Greater than 1. So in this case PLL is not locked because no solution point. Okay, what does it mean? It means what it is. What is this? That is frequency error. Means what? Omega in minus omega out. Okay, so what is the PLL condition? PLL condition. PLL condition is omega in equal to omega out. And we are saying that this thing is greater than 0. I mean, it is very high, means it is maximum, means high. Just let's say high. Sorry, you can say high. It is high. Since it is high, we can say that omega in is very high as compared to omega out. So now how to bring omega out close to this? We have to increase omega out. Then only omega in will become equal to omega out. Okay. So for this, what can we do? Let's write the equation for omega out. Omega out is equal to what? Omega free plus kvco dot vc. This is constant. This is constant. These two are constant. Only this we can control. So you have to increase vc. Then you can increase omega out. And if your omega out is increasing, so at a time omega in will become equal to omega out, and your PLL will be log. So that is one thing. So now what I want to discuss more, I want to make some plots and want to do some observation from those plots. Okay, let's see. So the plot was like this. Okay, so it was kind of like this. Yes. Hmm. This is phi error, differentiation of phi error, and this is phi error. Okay. Yeah. One more thing. If I'm taking this PD alone, okay. So your phase error is equal to what? Del omega 0 by t. It will, right? Okay. This will give frequency error, then you can calculate the phase error, right? So this is the equation, means what it is telling. This is an open loop. So if you are increasing the t, what does it mean? Your phase error will increase linearly. Okay. So it will increase linearly. So it is your phase error and it is t. Yes. And now why I'm telling this, that because we want to do some observation here. Okay. See, in open loop it is linear, but in closed loop it won't be linear. So that's why I plot it. I want to show you that it won't be linear. Why I'm saying like this? See, what is this? Time equal to 0. What is this? Time equal to plus pi by 2. And this is pi, and this part is 2 pi by 2, sorry, 2 pi. And mm, this one is minus pi by 2, this is pi, and yeah, this one is 2 pi. Okay, so you tell me that where the rate of change of phase error is high, maximum. You can see at this point the rate of change of phase error is very high. What is the rate of change of phase error? It means what does it means? Means phase is phase variation, phase error variation. Okay, so where is the value of this parameter is maximum? You can see here, here, and so on somewhere. And where is the minimum? Minimum is here, here. Okay, what does it mean? It means phase error is varying fast here. At what angle? Minus pi by 2. And at this point, it is varying very slow. Okay, so since at some time this phase error is varying fast, at some time it is varying slow, means it indicates that phase error is not linear in the closed loop. Okay, so let me show you here in this plot. I want to plot it. Okay, yeah, let me take red pen. So if it is minus 2 pi, and there it is minus pi 0 pi 2 pi. Okay, yeah, yes. So now what will happen from this is minus, this is minus, from minus 2 pi to, let me take some different color. Yeah, from this to this. Yeah, from in this part, what is happening? The rate of change of phase error is small. Okay, so it will take more time, right? And in this case, the rate of change of phi error is high, so it will take small time. Okay, so some here to here it is high, and then it is small. Okay, yeah, see there it is taking some time, delta c t1, and here it is taking t2. So we can say that t2 is less than t1, because in this case the rate of change of phase error from minus pi to 0 is high, means it will take small time. And in this case the rate of change of phase error is low, means it will take high time. So this t1 is high and this t2 is low, small. Okay, so I hope it is clear. Now let's go to the next point. I told you till now, I told you that we have to increase VC to increase the V out. Okay, to make PLL low, since the let me repeat, frequency error was very high. Since frequency error is very high, we have to increase omega out. For increasing omega out, we have to increase VC. And then I told that your PLL, uh, what was that? Phi error is linear in open loop, and in closed loop it's no linear. Because at some point it is fast rate of change of the phase error, and at some point it's low, slow. Okay, so one more plot I want to explain here, that so the previous plot I'm plotting first, that was phase error, and this is t, and this plot was somewhat like this. Okay, and yeah, so this was minus 2 pi, minus pi. Okay, and somewhere there it is pi, and there is considered 2 pi. Okay, so this t1 in closed loop I am talking was greater than t2. You can see in plot also it's visible, right? So now in closed loop what happened? It was non-linear, and throughout loop it will go like this because it's periodic, right? So now what? Now I want to plot one more parameter, that is V error. Okay, this is the thing. Now what is the varying parameter for this V error? That is phi error. Now according to phi error, we have to see how my V error is varying. Okay, yes. Hmm. Okay, so for this case, your phi error increasing, it will go like this, and then it will go like this. Okay, then again like this, and then like this, and this is t, and so on. So what it is showing, this waveform is asymmetric, first of all. Okay, This is asymmetric in case of what? When that is the case which we are observing, and we see this thing that it is asymmetric in nature. Means what? If you are taking average of it, it's a DC, it will have some DC value, right? Because it's asymmetric, it won't be zero. The DC value won't be zero if you are taking average of it. Okay, so let me go to the next slide. Mm, okay, so what I want to show you here, see, for PL look, what was the condition? That omega in must be equal to omega out. Okay, what is omega out? Omega out is what? Is omega free plus kvco dot vc. What vc should be what for this? See, what we want to make omega in equal to omega out. Okay, we saw that this frequency error is very high, and now we want this. So how much vc we required for it, that we are seeing. Okay, so it would be required that omega in is here, and then omega free will go on left side, and then divided by kvco. That much vc we need, then PLL can be low. Okay, but in reality, but what we are seeing, but vc is not enough large. It is not enough large, so that PLL can be low. Okay, so that is the thing. So see, what we saw V error. V error is giving some DC value, and then it will pass through the low pass filter, then it will become the VC. What we want? We want high VC. Okay, now how you will go to the high VC? That is the question. So now this is the DC, right? And let the DC value of okay, I'm plotting it again. It was somewhat like this. Sorry. Okay, it will go more down like this. So it was giving a DC value that I'm plotting with this red, and this is VP is the value. Okay, so this is giving VP, and now we want to boost this VP. How can I amplify VP? So to amplify this VP, we can use integrator, right? Since integrator have infinite gain, so we can use that and we can amplify this. And our problem is solved. Okay, we can't use L low pass filter to increase to amplify this, because the gain of low pass filter 1 by SRC is 1. So it won't be amplified, but we want to amplify this voltage error VP. So what we have to do, let me go to the next slide. Okay, what we have to do, we have to use a integrator. Okay, so what is that? There is V error, and now we are using integrator. Okay, and then we are getting amplified version of V error, KVCO by S. No, leave it not in S2 because I am keeping this integrator normal form. So let's keep it as VC only, and then feedback, and then some input, all that. So is it okay? Is everything fine now? See, you are giving V error and you are getting amplified version of VC. So everything is okay. Since your VC is high, your omega out will increase. And at a time, this omega in will become equal to omega out. So what was our issue? Issue was PLL is not able to load because the VCC is not enough high. Now the VCC is enough high, and our problem is solved. In reality, no. The problem is not solved. So why? So if I'm talking about at t equal to 0, what is the case? At t equal to 0, your VC equal to 0. Right? So what is your omega out at this time? This is omega free, because omega out is what? Omega out is equal to omega free plus QVCO VC. So when VC is equal to 0, this is cancelled out, so omega out is equal to omega free. So what is the frequency error at t equal to 0? That will be omega in minus omega free. Okay, and since this is the thing, your VRR will be equal to 0, since everything is equal to 0 initial time. I'm talking, okay, t equal to 0, this is 0, this is 0, and you saw that it is giving some at equal to 0. Okay, this is 0, this is 0, and I saw that VCO is giving omega free frequency. Then in next time it went there, it compared these two, and it gives some VRR value, which is some DC value. Okay, so at this time what happened, since it is giving in starting it is giving 0. Okay, and we want to amplify this DC voltage. Okay, so what we will do? Let me go to the next slide now. Yeah, so what will happen? Let me take pen. Hmm. So initially your V error will become, since there is will become equal to sinusoidal. Okay, at initial time. Since your V error is sinusoidal, I mean it's like this. So when it will go through the integrator, that time it will become 0 and your VC will become 0. See, I'm plotting. So this is your integrator and this is V error, this is VC, this is dt somewhat 1 by tau. So since it is sinusoidal, it will become 0 and then everything is messed up. So what is the solution for it? Let me clean this. Hmm. So initial time, what we will do, we will send this signal to two path. This is dt. Okay, so when it is sine, at that time, this will make it 0, but it won't make it 0. Okay, so your sine signal will go here and you will got some VC, which is control the your omega out. And in next step, what will happen? Sorry, there. Let me clean this. Okay, yeah. So in first step, I'm saying it is sinusoidal. So it will make it 0 and it won't make it 0. So this VC is not 0. And in next step, when your it will become like this in case of high frequency error. Okay, in that case, this will give a amplified version of the DC. Okay, and this will be high enough to increase the omega. This loop will work, and at the time this VC will become high enough to make omega out high. Okay, so why we are using this? This is called propagational path. At initial time, when your V error is sinusoidal, so that time it was not it was fully symmetric. That time if you are feeding these to integrator, it will make it 0. So to avoid that thing, we are using a propagational path. Okay, so it won't be 0 and after some time you will got this asymmetric sinusoidal signal, and this asymmetric sinusoidal signal will go through this integrator and you will got a high amplified version uh, of this DC value, and we'll got a high VC and your omega out can be high enough and your frequency error can be equal to 0. Okay, so what we have learned in today's lecture, we saw that what is the condition of PLL locking. So that was this thing, point 1. Point 2, if then PLL unlock. If PLL is unlocked, then what is how to make it lock? So the issue was here that VC is not enough high. So we have to increase the VC. Also, we find out that because of this condition, because of high frequency error, the this phase error is not linear. Somewhere it is fast, somewhere it is low. I mean the variation of the phase error, and we got the V error somewhat like this, which is asymmetric, and it have a DC value. Since it have a DC value and we want to increase VC, we have to amplify this DC value. So we know that we can amplify this with the help of integrator. Okay, so if we are using alone this integrator, that is not enough. We have to use one propagational component also. Okay, some DC value. Okay, because initially this V error is symmetric sinusoidal signal, and if it is sinusoidal and you are feeding it to integrator, it will make it 0 and your VC will become equal to 0 and your PLL won't be low. So for that, first we will, when it is like this initially, it will go to the through the integration path and it will become 0, but there is propagational path also. So there is propagational path also, integration also, and it will give 0, it will give some value, and these two will be sum up. So there is some value, it is not 0. And when you will got the asymmetric signal here, okay, so that time this will go through this and you will got a high amplified version of the DC gain of it, DC value of it, and you got high VC, and because of high VC you can have high omega out. Okay, so in that way you can lock your PL, and so there is propagational and integral path came into existence. So thanks a lot for watching this video. If you like this video, you can like it, you can subscribe my channel, and if you have any doubt, you can ask me in chat. Okay, thanks a lot. Bye.